Okay, so the uh, uh, content of this lecture was pulled from many different sources. I have mentioned a few of them here, and even uh, general articles about various security threats, etc. Right. So I try to be as comprehensive as possible, but uh, there are potentially new implementations that I might not be aware of. So feel free to, if you have, if you know anything that's not discussed here. So the types of attacks that we are going to see today uh, primarily are divided into four categories. One is covert channel based attacks. The second is side channel based attacks. Third is denial of service type of attacks. And the third one, the fourth one is sabotaging the entire system or a particular device, the degradation of the device itself. Now we'll go through each one of them. We'll spend some time, see some examples, some generic examples, some very specific examples, and try to understand what each of them is, right? So let's start with the covert channel. A covert channel, the formal definition is it's a mechanism that was not designed for communication, but which was nonetheless be abused to allow information flow in a way which was not allowed in the security policy. So the a typical any system you can take, there will be constraints on how the information flow would be there. There would be guidelines. Now, any channel that is subverting these can be potentially treated as a code channel, right? And these are intentional communication between a sender and receiver, right? And the system doesn't even realize that such a window of interaction is happening or is possible to begin with, right? And like I said, any communication channel that can be exploited by a process or a person to transfer information that is not adhering to the security policies well laid out by the system can be treated as a code channel. So these are the small, the formal way of looking at it. But in general, uh, a covert channel is any unconventional means of communication, and when it's used with an hidden agenda or an even evil intent, then it potentially becomes an threat for the entire system. So one of the example was as old as 500 BC in ancient Greece, right? Where to pass messages among various rebellion groups, what they used to do is they used to shave the heads of the messengers and write the information on the scalp, right? And then the messenger eventually waits till his hair grows back, and he would go to the destination where the uh, other group would again shave him or her basically, and read the message that was written. Now if you look at this whole example, because both the groups are being put under check, right? Uh, the kingdom, you can say, is in any case does not want the rebellion groups to uh, team up and launch an overall attack. And one of the primary things that would happen is they need to share the information and build more and more coordination so that the attack is eventually fruitful. To stop that, the administration can take steps to limit all possible methods. Now, what this particular covert channel is saying is, uh, instead of writing the message on a paper or any typical means, it is being written on the head of a messenger, which is not usually expected. Right. Another example is where is from the World War I timeline, right, where Germany used to conceal information by using microdots. Now, let's try to understand what's happening here. So let's say the higher authorities want to convey some message to the foot soldiers. So their captain would need to be sent a message. But what happens if the messenger gets caught in between by the enemy? Then the entire message would be uh, or the entire message is kind of lost, or it can be abused also, or something like that. So what the Germans used to do is they have come up with this notion of microdots. What these microdots are, they are small dots in the you can say in typical alphabets, uh, in which if you use a magnifying lens, you can get an inherent message. Now the letters like I, J, right, or the full stop, or semicolon, comma, etc. All these which are made up of dots can be uh, used for such a communication, right? The another example is a well established example proposed by Bell and Leigh Padula. I hope I'm pronouncing his name correct. So what they have come up is a model that is like a state machine to enforce access control in any government or military installment. Who can access some particular resource or a file and who cannot. To establish that, they have come up with a simple state machine, right? And it describes a set of access control rules which use security labels on the objects and the clearance for subjects meaning the people who are using these resources, right? The security labels, the most popular example is on the file it would be written as a top secret, or uh, red tape, or anything like unclassified, etc., right? So these labels on the files will help the subjects to move them around uh, and limit the access to anybody else, right? And so to enable the working of this model, two rules were laid down. One is that any subject or a person at a given security level may not read an object at a higher security level, right? Let's say the in an um, government office, or government office would be simpler. So let's say there are 10 levels of people, right? And we are labeling them with 1 through 10, 1 being the, let's say, the highest level officer, and 10 being, let's say, the simple security person, right? Let's say or a peon. Now if a person with the security grade, let's say 5, right, is given any file, and if that file is meant for people above his security level, means 1 through 4, he is not supposed to read it. Okay, that is the rule. And uh, here is another example where the researchers who are working on some secret projects, right, they would be coming up with a lot of new materials, studies, etc. They themselves are not allowed to view any files of their superiors, right? So they should not read up the level. The second rule is any person at any given security level should not write to any object at a lower security level, right? So here again, the researchers who create the content, right, should not create public files, etc., which are accessible to any layman, right? So the notion is no write down. So no read up or no write down. What it means is you can create content that can be read for the levels above you, and uh, you cannot read the content which is above your security clearance. Okay, now this in general is called no read up or and no write down rules, right? And what if we try to write up something and it already exists? Because we don't know, uh, we are not aware of what the uh, existing files are, because we don't have enough clearance. We try to write some new stuff and we send it above, and it is already existing, right? So what happens then? So based on the response, right, we can potentially figure out what is the content that is existing. We can give multiple tries to figure out what is there and what is not there. And this can potentially lead to can be treated as a covert channel. Also, another way to look at it is, let's say I want to convey some information to some secret information to a level, to a guy below my level, right? It should not be done. But how can I do it? Is we can be in sync to one another and do some actions that will convey the message. For example, uh, when we put a request to read some material and it is denied, for example, knowing that it would be denied, I do that process, and the observer will notice this event, right? And he can treat this event as, let's say, 1. And the next time I'll do the same thing, but it gets accepted. My action gets accepted. So then it can be treated as 0. So if I do this multiple times, the observer can potentially get information in a sequence of ones and zeros. So this can be another potential covert channel. Okay. So each denied operation is one bit of information which can be communicated across. Okay, so this is another popular example, and the BLA model was later refined quite a bit to handle such issues. And it is one of the popularly studied model to explain a covert channel, right? There are some set of rules, existing rules, and how can those rules themselves potentially be used to communicate information, right? And so a relatable example in computer system is, let's say there are multiple programs running, right? And typically the operating system assumes that the programs which are not uh, sharing any of the data, right? But and they are expected to run their simulations independently. But in the process of doing that, if they are able to communicate to each other, then the integrity of the system is questioned. Okay, now the different types of covert channels are storage based. The communications happen through the data that is written into a particular location, and the other process is trying to read this data either directly or indirectly. And the example simplest example are the printer queues or file logs. For example, two processes are there and they want to communicate. What one process, the aggressor, can do is put some file in the printer queue, right, for printing. And the other the spy program can check the printer queue. If there are contents in the printer queue, then it can be treated as a 1 or a 0. In the same way, file logs themselves can be used. So a particular file is is logged by the aggressor or the attacker, right? And the spy can go and check the permissions of this particular file, and if it finds that it's logged, then it can treat it as a 1 or a 0. Then there are timing based attacks also, where the time to perform an operation can potentially give information to the other party, right? So here popular examples that we are going to see are the CPU caches and memories, etc. Now, how does this happen is, let's say we have the shared cache resource, the last level cache, and the aggressor program can evict some of the blocks in the cache, and the spy program can try to read those blocks. If it finds them, then it can be treated as let's say 1, because the data is available in the cache, it is a hit. If it doesn't find them, then it can treat it as a 0. So these are cache based covert channel attacks. The same thing can be done either at the memory also, where in an event called the row hit or a row miss at a bank can potentially be used to convey information. And another a popular example of a covert channel is steganography, right? I'm going to give a small a demo of this, right? This what steganography says is it hides information inside a typical communication channel. The microdots can be interpreted as this, but it now it has the process has matured further. We'll look at it. And in general, what makes a good covert channel is that it should be hard to detect, right? So some of the covert channels, even though are known to be used, right? How they are being used, etc., can be completely implementation dependent. So like the steganography example we'll see, right? And then high bandwidth is like typically increasing the bandwidth usage increases the detectability. Why? Because the spy program can check the differences much more easily, right? And how easy is it to implement this covert channel, right? So it should be a very easy process for the aggressor and the spy to communicate or to observe the events. And the established notion is that both know how this particular channel works, right? And the last one is encryption. Even if the channel is exposed, right, how that data is being communicated is understood, but what data is being communicated might not be revealed. So even the message that you are the aggressor is trying to send to the spy, or the other way around, can be encrypted itself, and the supervisory system that is in place might know that some data is being sent, but it doesn't know what data it is, right? So one good example is the steganography, and in that the least significant bit of an image can be potentially used to send an information. So the basic idea is to replace the least significant bit of each byte of data in an image, right, with the data that we want to send. And usually a color image consists of 24 or 32 bits of data per pixel, right? So we can go and change some of these bits, and the receiver would extract these bits and try to reconstruct the data. right? So replacing only a few bits at the LSB side will slightly alter the image, but it might not be so visible also to the naked eye. And the more number of bits we are trying to change, the more the original image gets distorted, and the more is the likelihood of it being detected. And in general, there is a rule that we should not be changing more than 25% of the data. So, if let's say here is a image, a commonly sent image, there's no threat involved in it. It's just a rabbit sitting in the snow, right? But there is one bit in each of these the pixels in this image that has been changed. And when the spy tries to extract those sequence of 1 bits and reconstructs an image, it has resulted in a aircraft, right? Now, when 2 bits are changed, still we can observe no visible distortion in this image. But when we try to reconstruct, more and more details are being observed by the spy. So, and when we change 4 bits, the image is now slightly distorted. Here you can see some of these places, and here also, right? And the reconstructed image is much more clearer now, with a lot more details. So we can extend it further. So if we change 5 bits in each of the pixel of the source of the source image, then it gets distorted further. But eventually, if we, let's say, change 7 bits of hidden image of the original image, right? So it can get completely distorted. So steganography tries to find the exact trade-off on how many bits we can potentially distort, and how many bits at minimum are required to reconstruct the message at the receiver's end. So this, if you look at the setup, what we are trying to see, the threat model is, let's say there is a system in place which is trying to monitor such images of aircrafts, etc. And it will definitely ignore if it sees a rabbit, because it's an animal, or non no threat kind of thing. There is no explicit information that is being passed. But the sender, knowing that such a system is in place, still wants to communicate the details of the aircraft, can use this technique. And this is a very well-known example of the covert channel. So with that, I'll pause here for a few questions. Any questions till now?
Yeah. Hi, Kalyan.
Yes, Pratham.
So, for covert channel to be successful, is it that the sender and the receiver should already be in the sync, right?
Yes, yes. Otherwise, it sync in the sense it depends on the event itself. Let's say if uh, the sender has sent the information, but the receiver has more flexibility on when he can observe that, right? So uh, it depends on the exact time criticality. But yes, there should be some common rules in place saying that, let's say uh, we both want to communicate, right? And we have our utility block. I would say that I'll place a group of red chairs in the canteen at some particular location to send you a message that yes, today there is an exam. I'm just saying, right? And I'll tell you to go and check at 12 o'clock in the noon, right? I can go and make that arrangement well before in the morning, or just by just a few minutes before, and you can check anytime after 12. So the notion of time here is not so tightly bounded, but there is a understanding that I have to complete my work by 12 noon, and you can look and make some interpretations after 12 noon. Does it make sense?
Yeah, yeah. Mhm. But
Right.
if there
So
is noise, if there is some noise in just like in the system, so I think there will not be that much flexibility that even the receiver has to be quite vigilant about it.
yes, yes, and even the sender also has needs to be aware that there are potential elements that can interfere. So this happens over across multiple trials also.
Ha ha, yeah, yeah.
Yeah, it's not one or zero kind of thing.
Right,
Yeah,
right, right. Yeah. Okay. Thank you.
yeah.
So in an image, there are many ways we can send in. Like we can change the contrast, or there are other things. Like there are already three channels of the colors and all. So
Mm-hmm.
such a covert channel would be very difficult.
I'm sorry, sir.
So like
Detecting the code channel.
yes.
Yes, yes, yeah, yeah. That's why I have given that example. It is very well known that it's a very good code channel. What you said is correct. There are potentially many parameters, metrics of an image that can be changed.
Hello, sir.
Yes, Rohit.
So basically, in a covert channel, you need to have at least two parties, right?
Yes.
So one guy should, I mean, like clicking, I mean, only one party covert channel is not possible, right? At least two should be there, no?
Yeah.
Like, okay. And so the
Yeah.
difference between this and side channel is that in side channel, we are just making use of some kind of flaw in the design or something. Is that it? The main thing? For example,
Yes.
the
So even in side channel, there are two parties, but one party is the victim himself.
okay, I mean the victim is not knowingly leaking info like in covert
Right.
chat.
Right. Right.
Oh, thank you.
Yeah. Anyways, we are going to look at side channel details a little more now. Any other questions? Okay. So in that case, let's continue. Okay, I didn't realize that the presentation stopped. Okay, I hope you all can see this slides, right?
Yes, sir.
Yes, sir.
Okay. Uh, Now coming to the side channel is by the definition, like Rohit was asking, that it is an unintended channel emitting information, and the primary reason for that is some of the physical limitations itself or the implementation flaws itself. And the attacks which are based on this side channel, what they primarily do is look for these flaws in the implementation or the limitations of the existing system and try to extract information from that. And this does not depend on the theoretical weakness of algorithms that are being established, etc. Right? This is a slight difference when we when we compare with covert channel. So the covert channels can still uh, face lot of implementation difficulty if the security system in place is very robust, right? So passing the information will become more and more trickier. But side channel doesn't have anything to do with the implementation, the sorry the uh, effectiveness of the rules in place, right? So it is more to do with how these rules are getting implemented, etc. And its side channel is also not a brute force attack to get the information, etc. Okay, it does not do uh, forceful attempts to gather information. So it silently observes some phenomenon and tries to interpret what's happening underneath. Okay, some of the points that the that can be potential side channels are the time of the event, right? The time it takes for the event to happen, right? And the power consumption when some particular process is running, or uh, any action to takes place, right? And speculation can be potential side channel, right? And the temperature when a process is running can also be a side channel. Then the acoustic means uh, the sound that gets generated can be a side channel, or the electromagnetic radiation can also be a side channel, right? Now what it means is the attacker can potentially observe one or more of these parameters and try to infer uh, what is being done. Okay, now let's look at some of these, right? And understand how it gets implemented and what it uh, what it can potentially convey. So let's start with the timing side channel, right? The timing side channel works by observing how long a task takes to complete, right? Now these attacks obtain information from the point from the point that an algorithm can take different amounts of different amounts of time based on its input. And if the input is the secret data, then making some inferences on the working of the algorithm, right, can potentially leak the secret data. We're going to look at a couple of examples here. And this, if the secret is revealed, then it can be uh, uh, very devastating. And these side channels are um, more dangerous than covert channels because they do not require that the attacker and the victim necessarily share the same resources. Okay, now let's look at an example. So many of the standard algorithms for addition and they use addition and multiplication. And let's look at how these addition and multiplication can also leak some information of what they are processing on. So let's take two numbers, 325, and let's try to multiply them. And let's also take another set of numbers, 7 and 25, and see how we can infer what is being done underneath, right? No. So the bit level representation is like this. So 11 stands for 3, 111 stands for 7, and 25 is 11001. Okay, now let's assume that each step of the algorithm, right, takes 1 unit of time. And if we want for the 25 times 3 operation, what we would get is we need 5 units of time for multiplying the LSB1 with the 5 bits of 25, right? And then another 5 units of time to multiply the second digit 1 with each of the digits in 25. That will be 10 units of time. Then we need one additional time to shift the second result. So that is the typical multiplication that we do, right? Shift and add. And let's say to add these 6 bits, we take 6 units of time. So overall, we need 5 plus 5, now 10, 11, and and plus 6. So 17 units of time would be needed to multiply 25 and 3. Now, when we look at multiplication of 25 and 7, right, the same process here. So to multiply each of, with each one in different places, we need 5 units and total 15 units of time just for multiplication, and 2 units to shift the second and third multiplicand, sorry, the partial product, right? And then to add we unit 7, we need 7 units of time. So it would effectively need 25 units of time. Now, if an attacker is trying to observe how much time this multiplication is taking place, right, he can try to make some inference on the data that is being multiplied. Okay. Now, as you might guess, this needs lot of focused information gathering, right? It's not that we can go and check the time for each multiplication or each addition, or the a time for each to calculate the product of two numbers in general. So the attacker has lot more knowledge of how the underlying system is working. Okay. Another example, which is a real-time example, actually it was well established. So there is a libgcrypt library, right? And in that there is a function square and multiply, right? And here a part of that function is given, and as the function name says, it is trying to calculate the square of an number, and it will also do the modulus operation and then do something more based on a key. Okay. Now this in general implements what's called modular exponentiation, and it is quite commonly used in RSA and other algorithms, right? This particular function. Now, like I said, this algorithm essentially takes the square of a number and calculates modulus. Okay. And after that, if you look at line number 58, right, it's trying to see the key, right? It's trying to use a variable called key, right? And based on that, it will again decide what to do. If it's not equal to 0, when it is ANDed with 1 at the MSB position, right? If it is, then it performs something. If it is not, then the key is left shifted by 1, right? So what is happening is based on the digits of the value of individual digits in key, we will decide whether we have to execute lines number 59 through 63 or not. So this can potentially give us a lot of information on what the key is, right? So every time a bit is set in the key, right, this loop iteration will happen and it will take more time. But if the key, if the bit position is 0, then we'll directly go to the next line, which is 65, right? You see a difference here. If the value of key is in some particular position is 0, then after line number 59, we'll directly go to 65. Otherwise, we will have to go and execute 60, 61, 62 also. Right now, we can differentiate the time more easily, and from that we can try to regenerate the value of key itself. Okay, and this can quickly leak lot of information about the key. So there is a risk of this side channel And what we are doing this is a very high level observation that the time of operation itself is changing based on the input, right? So I'll pause here for any questions.
So will the side channel person know the code?
Yes, this is a standard implementation. Only from that he can interpret, right? All he has a lot of details and he doesn't have the key that
Yes,
is
sir.
used.
I get
Yeah,
it.
yeah.
So side channels are more vulnerable for ASICs. Is it so?
Mm, why do you say that?
So hardware is fixed, and the same competition will happen again and again.
Yes, that is true. But in ASICs, we can potentially include more. Um, yeah, but that will not help. It will only help the covert channels. Yeah, seems like for ASICs, it's little more. Uh, yeah, it's easy, I should say. Is that what you're trying to convey?
It's a more vulnerable, like
Yes.
easy.
Yeah, yeah. Yeah.
So in the previous slides, there was something known as speculation. So what is speculation?
I'll come to that.
Okay.
Okay, I'll move on. Whenever you have a doubt, just pause me. Another other possibilities of these timing side channels. Uh, we'll look at a couple of them now. So what we have seen in the earlier example is that based on let me go here. Based on the point that whether this branch is taken or not, we are trying to interpret uh, the value of the key. Now, not all implementations might need such resolving the information based on a branch. So there are other possibilities also, like the instructions that are getting used, they themselves will give information. For example, the multiply divide operations typically will take more time than add and subtract. So this can be potentially used as a side channel, right? The and there can be a timing variation based on where the data is located in the memory hierarchy. For example, if the data is readily available in the registers, no problem. Otherwise, we'll go and check at various levels of cache, and it can uh, give us a more quantifiable change in the timing of getting the data, right? If we eventually go to the disk, then it takes tens of microseconds to get the data. So this can be a potential side channel. And one example of one other example of the timing attack is in the typical implementation of SSH, right? When you try to do a remote login into another system using SSH command, it was shown that the password we enter when we want to kick off this session can be leaked based on a timing attack. So it was established right in 2001 itself, and the paper name is Timing Analysis of Keystrokes and Timing Attacks on SSH, right? So I'm not going to dive into the depth in this paper in depth, but what the authors were trying to say is the implementation of SSH is like that. Whenever you enter a character, it is packed and sent to the destination server, and the delay in and delay of the user in entering the characters can potentially be used to interpret what data it is, right? And they demonstrated that guessing the password based on observing the timing, right, can give a uh, lot of information, and eventually they are able to get the passwords much more easily. Now let's look at the power side channel. And just like timing, where we were looking at the timing of an operation, here what we are going to see is the power consumed for an operation and try to interpret what is happening, right? So the power side channels leverage the fluctuations in a machine's uh, power usage when performing different operations. And it's well known that the power that is consumed is different for different instructions, right? For addition, multiplication, the loads and stores, for branch or other shift operations, etc. The power consumed will be definitely different, because the underlying circuit that is getting activated and used, right, enabled and used, is different. And it can also depend on the operands of the instructions, like we saw in 3 times 25 and 7 times 25, that example. So 7 times 25 can potentially consume more power than 3 times 25. Okay, that can also give some information on, yes, there are two, there's a larger numbers that is being used to multiply, etc., right? And for to enable the power side channel attacks, the adversary will require physical access to the machine, and this is needed so that he can measure the exact power usage, right? And some of the traditional attacks use the oscilloscope to measure the voltage fluctuation, etc., and from that they interpreted values. So the attack model, like I mentioned, is that they have physical access. And another example here is that the adversary can control, can have access to the plain text or ciphertext. Now, what are these plain text and ciphertext? Is plain text is a simple message, and ciphertext is an encoded message based on this plain text, and it is encoded using a key. Now, the attacker wants to get an idea of what key is being used to generate this ciphertext, right? So this is the goal on of this attack, right? Now the plain texts are fed into this particular crypto device, right? And it uses a key, and it will encrypt the message, and it gives the ciphertext. Now, by observing the power fluctuations during this process, the attacker can potentially get what the key that is being used. Now, to for all this to happen, there are different methods, right? And they are divided into 3. One is a simple power analysis, right? Just by looking at the power trace, the adversary can make some some inferences on the information, right? And there is differential power analysis, right, where the adversary uses some statistical techniques to learn this information, right? These statistical methods can be difference of means or correlation or error correction, etc. Third one is high order differential power analysis. And what this will do is it will consider the power readings from different sources simultaneously, and tries to interpret the information by and it assumes that the data that is being collected is synchronized by time. So it is a little more complicated to stage, but it is much more effective to decipher the information, right? Now, a simple power analysis, I'll just give an example. Most likely we are not going to look at power based attacks in this course, but I wanted to give a quick example on what it might look like. No, so here is the power reading, right, that we are seeing in an oscilloscope, right? Whenever a square is being done, right, it is consuming some power, and then if we are trying to multiply, then we are seeing some different power, etc. Okay, now from this itself we can interpret some information. How? If the if the power pattern is something like this, so we have a square followed by a multiply, so it can be interpreted as a 1, right? Again, in the second set we have a square followed by a multiply, so it's 1, and next we have a square followed by a square operation, right? I'm interpreting that it's a square by looking at its power consumption only. So the third bit can be 0, and the fourth bit can be here it's 1, fifth also is 1, sixth is 0, etc. So here we can interpret a sequence of bits that are being used for this operation. Okay, and these bits can be the key also, and even if the key is of arbitrary length, this simple power analysis can potentially give us insight into the key. Okay, so I'll pause here. Any questions with power side channels?
Yeah, hi. So I don't have any question regarding this power analysis, but I have one question regarding the previous one, the side channel.
Mm-hmm.
In that, you mentioned about the timing-based attacks. Just out of curiosity, if we know that these timing-based attacks are used, so why don't we drop, the instruction from the instruction set architecture, which is, basically giving them that amount of resolution at the timer level? Like,
Meaning, just as an example, let's say multiplication is taking 10 cycles and addition is taking 1 cycle. So you are saying because there is a lot of difference, we'll drop either add or multiply, is it?
no, 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 no.
Hmm.
No, the instruction which is helping them to analyze the power, the timing difference.
Meaning?
Uh, just like it has to know, right? This came after one cycle, or it came after 10 cycle.
Mm-hmm.
So actually, this is we are looking at nanoseconds and microseconds, right? So the
It's even
resolution of the
smaller than that. Yes.
it's even
Yes.
smaller than that, yeah. So why is that the scope resolution, the timer resolution operator, like it's very difficult to use it, right? So
Yes. So that and we have much like you are saying, we have some potential defenses for this side channel. They're well established. I'll touch upon one or two of them even in few slides. Okay, we can
okay,
discuss your question again there if it's not
okay,
clear.
fine,
Okay, yeah.
yeah.
Okay, so uh, I'm moving to the next speculation side channels, right? And so I'll give you a very, very high level view here because this needs some advanced, microarchitecture details like uh, out of order execution, etc. We are going to look at these in the second half of the course anyway, but for completeness, I am including here, right? So in almost all the current day processes, the out of order execution is being used and speculative execution is being used, right? Speculative execution, what it primarily is, uh, as you know, whenever a branch instruction comes, we don't know where it would head to, so we use branch prediction, right? And branch prediction, because it's a prediction, can go wrong sometimes. So what happens is when our prediction is wrong, will flush the pipeline and get the correct path, and we'll restart the execution, right? In speculation, what they do is to avoid the time lost during due to the instruction flush, etc., right? They say that we will go ahead and speculatively execute the I think I already covered the speculative execution, sorry. So in the speculative execution, the notion is based on the prediction itself, we'll go ahead and continue with the predicted path, and if it goes wrong, then we will flush the instructions. it is heavily based on the accuracy of the branch prediction itself. If the branch predicts correctly that, okay, uh, uh, this particular branch will be taken, right? The speculative execution concept is it will go and fetch the instructions in this taken path and starts executing them. Okay, out of order is in the typical pipeline. What we do is we'll execute one instruction after another. Now let's say that we have a multiply instruction and it takes 10 cycles, and just after that we have an add instruction. Now if we want to wait till the multiply instruction gets executed, then the add instruction is also waiting for 10 cycles effectively, right? So what out of order execution says is, if there is no data dependency between the multiply and add instructions, we will go ahead and execute them in parallel, right? What it means is the add instruction execution is starting before the completion of multiply instruction. That's why it's called out of order. Okay, now both of these are very complex mechanisms to implement, but very effective, and that is the reason they are implemented in almost all the current day processors. So if you're not able to make much sense out of what I have told in the past few minutes, don't worry, we are going to touch this point again. Right now, both these optimizations, right, help to maximize the usage of the CPU resources, which means that if there are multiple functional units lying at our disposal, we'll try to use them as much as possible in parallel. And the moment we say we'll try to use multiple of them simultaneously, then the overall performance can also increase. Right now, the wrong path execution, like I said, sorry, if we know that the path we have taken is wrong path, then we are going to flush them. But these instructions that are getting executed before you have resolved the branch, you can say them as transit instructions. Now these excuse me, and these some of these instructions, right, when executed in out of order and are still not confirmed that this is the correct path, etc., can leave some prints or onto the primarily to the memory that has been exploited. For example, we have based on the branch prediction, we have started executing some instructions, and let's say one of those instructions is load instruction. So what we do is we go and try to fetch data for that particular load instruction. So the address will come to, let's say, the L1 cache, and this let's say the data is not available in L1. So we eventually get it to L1, and then we'll go ahead with the rest of this particular load instructions execution. Now, if when we realize that this instruction is not in the correct path, we simply flush it. But what happens is the data that we brought into L1 because of this instruction will remain there. So this data that is now lying in L1, which should ideally not be, can be a potential side channel, right? So these instructions can either be used to create a side channel or covert channel, right? And the very popular examples that we keep hearing from the past few years are the Spectre and Meltdown attacks. Okay, now I'm going to spend more time on these attacks, maybe a couple of classes in the second half of the course, so don't worry. But what I wanted to convey is these inherent microarchitectural features themselves can be potential side channels. Okay, not only the power or the time. Now another side channel is acoustics based attack, right? Let's look at an example, right? In the paper that was published in 2013, it's it's actually a technical report, right? So what the authors have showed is they were able to extract a 4096-bit RSA private key from a laptop. And how did they do that? Is by looking at the noise that the laptop or the computer has generated, right, to perform an operation. And this noise was used to derive the key for decryption. Okay, and they actually demonstrated that the information just because of this noise has helped them to decode some of the ciphertext within a few hours, right? It's that effective. Okay, and to demonstrate that their attack, what they did is they placed a microphone next to a target laptop, right? And they started noting down uh, the the noise that it is generating, sound it is generating, and they have made some interpretations from that. Now, it might sound all too high level, but what the key point here is that the attackers have a lot more details on the implementation, right? Just like the power and the timing, here too, what aspects generate the noise, etc., need to be uh, carefully measured and quantified, right? And another attack was also demonstrated in the same paper, wherein they were just trying to uh, uh, infer the key by touching the computer chassis itself, means the CPU cover, basically, right? So, and the signals that are generated by various components, right, are uh, picked up by the power supply, right? That were it had some components which will pick up these acoustic signals, and it was able to decipher some information. So again, for completeness sake, I have put it here. We are not going to study acoustics based attacks in this course. Okay. Now, let's look at some of the mitigations of timing side channel attacks. Now, one of the question Prathamesh has asked would be answered here, right? So, what are the mitigations possible is randomize the flow of the program, right? Or insert some random noise, or padding the data so that all the data looks more or less uniform, that the execution will also look uniform, right? And there is a need to come up with constant time algorithms, and this requires that we rewrite the code, and there is a need that we need to come up with constant time instructions, meaning that the example we took, that add would take 1 cycle and multiply, let's say, takes 10 cycles. That kind of implementation is should be discarded, right? Or more or we should come up with efficient implementations that add and multiply will take more or less the same time or comparable time. Okay, in that case, the side channel based attack that we discussed earlier will be useless. Okay, so I'll pause here. Prathamesh, can you ask your question now if it's not answered?
Yeah. My question was, so there is this attacker. So it has to be very precise with, like, all these attacks. They are basically timing channel attacks, right? So they should have a timing resolution operator that after this many cycles, I again have to go and probe the last level cache to see whether which blocks are present, right?
Hmm.
So in that case, why is the instruction set architecture still just like there is one instruction which is known as CL flush,
Hmm.
which is used to flush the data, and if that block is shared, then an attacker can potentially leak the information of victim, right?
Okay.
So this
Okay.
kind of instructions are still there in instruction set architecture.
Uh,
Uh,
okay. That is good point. But why was CL flush included to begin with?
Actually, I have no answer to that, but
Okay.
I have seen, I
So
have not got any
um,
answer. Yeah.
that's okay. Let's try to understand that, right? Uh, what happens on a page fault?
Yeah, we have to go to the main memory
Disk
and again.
and no, at the main memory. We're already at the main memory, and we realize that we need to go to the disk and get the data.
Right,
Right? It can take few microseconds to milliseconds, or even few seconds if the disk is very slow. Right? Now,
right,
what will the processor do in the meantime? It can't wait for the data, so we do what's called context switching. Right?
right.
Now, the L1 cache, which was holding the data of the previous thread, right,
Yeah,
now needs to be used by the next to hold the data of the next thread, right? Just like we are trying to flush the instructions that were wrongly executed, we need to flush all the contents of the L1 cache so that it makes space for the new cache, I mean new threads data.
okay. Mhm.
So in these contexts, the operating system itself will do the flush of the cache,
Right.
right? And this is very much needed because at L1 we might still be using the virtual address to index into the cache, etc.
Ah, yeah. Mhm.
Yeah, but it's not needed when we talk about LLC level, right? Because we
Yeah,
are
yeah.
using the
Uh,
physical address.
Physical address, yeah.
Yeah.
And even if it is there, then the operating system should have its privilege, right? Not the user.
Uh, that is a good point. Um, at this moment, I'm not able to come up with any example where the user program will itself need a flush. Hmm. But don't you think any program would need it? I mean,
Uh, I mean, I'm not able to, again, comprehend that why it is needed to the user.
hmm,
Uh, if there is some concept like the memory is not free, right, as you rightly mentioned about the L1 caches,
hmm.
so then the operating system should take the control, right? After the context switch, it will flush all the
Ah,
cache contents.
yeah, OS is the one which will do the context switch.
Yeah,
Switch, right?
yeah,
Huh.
yeah. So why is it still available to user? I mean, although not all architectures support it, but still there
Hmm.
are some which are still supporting it.
Hmm.
uh, Yeah, so
Okay.
actually, I also don't have any clue that why still, but it must have its own reasons that they are still providing it.
Huh. Yes. So, yeah, we'll dive a little more into this, when we are discussing the cache-based, timing channel attacks. Okay.
Yeah, yeah,
At
sure,
that
sure.
point, we'll try to understand the history of the CL flush a little more.
Yeah, yeah, sure.
Yeah. Yeah. Okay. Any other questions? Okay. Let's move on to the mitigations that would be required. Possible mitigations for power side channel attacks. Um, for power side channel attacks, the synchronization is very much needed. So we should try to uh, make it as difficult as possible, right? So we can uh, modulate the CPU frequency that can change the power consumption, right? Or add delays to the program, or randomize the execution of the program. And their approach is to make the power usage uniform, just like we are saying that all the instructions should take more or less the same time. Here we should try to come up with circuit designs that would, uh, help us to bridge the gap between the power consumption of different instructions, and otherwise deliberately add noise to the power consumption. Okay. And one of the thing that is widely used now is to change the cryptographic keys often, so that even with the power side channels, if somebody is able to interpret the key, that will not be effective much, right? And the other type of attack, now we are moving on to the denial of service attack, right? What we saw, the first one was covert channel, second is side channel, and this is denial of service. As the name says, right, it tries to uh, create hindrances to the victim program, or the victim himself, to access any particular resource. Okay. Now uh, one of the global threat that uh, can potentially happen is, let's say, two neighboring countries are at war, right? At the time of war, if the let's say there is a common river flowing between the countries, and at that time, if the uh, water resources are uh, barricaded by one country, the neighboring country even definitely suffers. So this is a typical denial of service attack, right? Or there was another brutal tactic that Germans have used. uh, what it was is, when they knew that they were losing the war, right, and they eventually have to retreat, or means that they will lose the ground they have occupied. What they did is, before they left, they burnt everything down, right? They poisoned the water resources there. So even if the other guy wins, he has huge task to rebuild it. So this is the tactic they called scorched earth. It was very bad, and later this kind of practices were you know um, uh, branded illegal by the UN. But yeah, this can also be potentially treated as a denial of service attack. Now, what we are trying to do here is, any shared resource here, in any hardware that is being shared, right, can be potentially used to stage an attack, right? If we keep the hardware busy enough, then the other programs will take time to access it, right? Now, the threat model we have here is that the adversary and the victim both are having access to this shared resource. And this is a common scenario whenever we are viewing the hardware as a shared resource, right? Like, even in cloud, um, we have the hardware as a service kind of setup. So if we have any program that is eating up the storage, right, or it's keeping the network busy, so all the other programs will slow down, and the effect is, like I said, is a drop in performance or the quality of service of the victim program, etc., right? And what do you think would be required for mitigating such denial of service attacks?
So it is something like a virtual gateway, and to access the shared resource, or changing the. It's like it's done in the networks and all, internet and all.
Meaning, I didn't get you. Can
So
you
like
explain further?
they like we can access a server, or a website through a
Mhm.
VPN. So we continuously change the virtual ID of the VPN such that it's not trackable, and if it's not trackable, there cannot be a DOS attack on it.
Okay, that's good.
So
Good
something like
example.
that.
Yeah, yeah. Any other examples? So I think in the last week's discussion we were uh, talking about a powerful technique, right, to disrupt the side channel attacks, which is the randomization. Here too, we can do that. The hardware resources that are getting mapped to the mapping itself can be randomized, so that the attacker would need to restart the attack every time there is a remapping that is happening. Make sense?
Yes, sir.
Okay. Any other defenses that you think we can build?
Sharing the resource in a round robin fashion, maybe in some time
Hmm.
quantum, we come up with
Good,
some kind of
good,
scheduling.
good. Yes, it's called fairness, right? We
Yeah,
want
yeah,
to make sure
fairness.
that all the users are getting equal opportunity to use the shared resource. So many of the fairness algorithms are already in place, and they need to be refined to handle this DOS attacks a little more. For example, Prathamesh, you have mentioned Damaru yesterday, right? Now, what Damaru is trying to do is, so for others to quickly understand, so it is for a shared cache, and it is a denial of service attack on the shared cache. What what the authors are proposing is they have potentially created a program that is keeping the LLC busy, that the victim program execution has slowed down quite a bit. Okay, now how can we break it? By ensuring that in any time window, right? Let's say we take a window of 1,000 cycles. If we make sure that for every 1,000 cycles, we need to definitely service others programs, right? Then the Damaru attacks effectiveness will reduce.
Yeah, right.
Right. So uh, and that was, I think, Upasna was there when we read it for the very first time. We were actually having a laugh at it, saying that the simple fairness based implementation would stop it.
Yeah, yeah, right. Actually, I think there is a trade-off between performance and fairness there.
Huh.
That,
E-
yeah,
yeah, see, most of these mitigations that we are talking about have performance implications,
right.
definitely.
Yeah, because in the Damru, what they are saying is they are creating an application
Hmm.
in such a way that it will be 99% miss at the level 2 and
Hmm.
99% hit at the last level.
Hmm.
So
Hmm.
basically, they are grabbing all the resources by using cache hit as an medium.
Hmm.
So if it is a cache hit, and if we introduce the window which you are talking about, that will definitely stop this denial of service. But as the application itself requires lot of cache hits, and if that is denied, then I think the performance will be compromised. So we have to come up with a middle ground there. But yeah, that will stop denial of service.
Yes, and this fairness-based scheduling is not new. Also, even in let's say even the OS does something like that. It cannot deny execution of one thread because the other thread continues to use the resources, right? So
Right.
round robin based allocation is done at many places.
Right. I think at the DRAM queues also it is used, right?
The scheduling there it is. If you simply go with first come first serve, that itself will break this, isn't it?
First come first serve. But then I think the attacker will have great chances, right?
Yes, that is there. But I'm saying that it will not stop the access of the victim. It will slow down. But when we say denial of service, it literally means that we are not allowing him to access it all.
Ha 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 ha.
So things
Yeah.
get queued up. But on top of it, what the fairness would do is after every, let's say, time window, it will make sure that others also get a chance to use the resources.
Yeah, right. I think Kalyan, what that Damru paper was suggesting, na, it is a little
Mm.
bit subtle there. Actually, I
Mhm.
was also kind of confused there, but the point is, na, the importance is that the code is written in such a way that it is not going to fit in L2 anyhow. So
Mm.
if there is a victim application, right? So it has all the cache hierarchies and all the accesses will be filtered there, right?
Mhm.
So the accesses to the LLCs are filtered by the upper level, but
Mhm.
the attacker code is written in such a way that it is 99% it will be missed at the upper levels.
Mhm.
So if we introduce fairness here now, so what will happen is the read and write queues or all the MSHRs, the attacker's MSHRs will be queued up. So the performance
Mm.
loss is I think huge here.
For the attacker or the victim?
Then for the attacker, if we
Mm.
introduce this
Yes,
queueness,
yes.
fairness.
Yeah, fairness. Yes, yes. So, see, we need not. Somebody put a message. Can somebody read it? I am not able to see the screen there.
Okay, Upasna has written, we realized that Damru was very specific to memory access frequency.
Mm. Oh, okay, okay, okay. Yeah, yeah. So that's what I was trying to explain. That we need not look at the hits, misses, etc. We are just going to look at the accesses. Okay. Now, uh, in a window of let's say 1,000 cycles, assume that in each cycle we can service one request. The cache LLC controller can potentially serve 1,000 requests, right?
Right,
Now, if the fairness policy says that in this among these 1,000 requests, I can at most allot 600 requests to one thread, but all the other threads should definitely get 400. I'm just
right,
giving an example. Or
right,
let's say there are 4 threads at any given moment. They and everyone will get an opportunity to use 250 of these cycles.
right.
Means 250 requests of each thread can potentially be serviced by the cache. So that also is good enough.
Yeah, yeah, yeah.
Is it important to detect the DOS attack? Like there is a DOS attack.
What happens, ish, in this sense is you are trying to do some work and you're not allowed for one of the common things that can happen, of course it's not deliberate, is during the new year or some or festive time, the mobile networks look very bad, right? We are not able to connect the calls, or the calls get dropped, or the messages don't reach on time, etc., etc., because there is a huge congestion on the network. Now, if the congestion is being created deliberately, what will you do? Ish?
So like we discussed some of the methods which we can like use fairness or
But your question is, should we address it or not? Isn't it?
yes, sir. So like
Huh.
it is like means if we know that where the traffic is coming from, the DOS attack is coming from, we can switch off their access specific to that program,
Hmm.
and but again they can then create another DOS attack from other
Other thing. Yes.
or
Yes.
other program.
That's true. That's
So
true. If you can, blacklist some particular application, good enough, but it might not be possible all the time. Yeah.
yes, so sir, but okay, means detection is not a priority in a denial of service attack.
Detection is not priority, but how will you know that there is a DOS attack, right? If you see a substantial drop in the performance of a typical program, then it means that there is something wrong.
Okay, means it is
Won't
like
it?
it is not detectable that easily because anyways some users have to make accesses and
Hmm. Yeah, but in general, we need to make the system robust enough to, handle all the requests fairly. Make sense?
yes, yes, sir, because
Hmm.
anyways if the DOS attack like it is using our hardware resources and there's no output of it, it is just
Hmm.
wasting the usage of the hardware resources.
Right. Right.
Yes.
Okay. I think this is my last slide, so please bear with me. So this is the sabotage or device degradation kind of attack, where the threat model is there are trojans. It can be hardware or software trojans, means malicious components in your system that can sabotage the entire system, the working of the system, or they can leak the information from the system, right? So the the various examples are like we can change or destroy the data, right? So ransomware attack that we saw belongs to this category, wherein the data is getting changed and it might be destroyed also because it's getting encrypted, and if we don't have the decryption key, it's more or less lost, right? And row hammer we will see in the DRAM based memories, where we are trying to uh, change the data in the neighboring rows, the victim rows, by aggressively accessing one particular row. Okay, so again here we are destroying the data that is stored in the adjacent rows. Then we can destroy the hardware itself. Now it might sound too naive, but it will become more and more prominent because we are using a lot of non-volatile memories, and many of them have limited lifespan. Okay, now another example is a very trivial example here. Okay, let's say we have placed a CCTV camera, okay, and somewhere, and it is still it's placed in a remote location. All it's doing is it's trying to sense some movement, and and it will, the entire operation will be triggered only when some movement is there. So it is optimized for power consumption because it's in a remote location. But what if somebody deliberately goes and moves around it? Then the device will be on for most of the time, and it will run out of the battery. So somebody has to come and replace the battery very often. So one of the most easiest examples we can say, right? But more damaging would be to destroy the internal hardware or the memory chip, right? Even your SSD has a very limited lifetime. So you just try to if you have a program that just keeps writing junk data, right? So it will eventually destroy the memory cell. And if we are exploring STT-MRAM or PCM or 3D crosspoint kind of NVMs, then their lifespan is even lesser than the typical volatile memories. Then the entire hardware becomes unusable. Okay, another the attack would be to use these trojans to increase the temperature, or ambient temperature, or the power consumption of the device itself, so that it can eventually burn out. Right? And one other is to compromise the quality of the end product. Now here I will refer to the reference one by Jacob Gatlin, right? What they have demonstrated is, with the 3D printing, there are a lot of parameters that can be tampered with, so that the end device that got eventually built using this 3D printer will be of low quality, either the thickness of the material, or there can be some gaps across the layers, etc. So they demonstrated that for additive manufacturing, meaning that it will be in multiple layers, etc. A product will be built. They have multiple opportunities to sabotage the entire process and eventually create a low quality product. Okay, so all these would come under sabotage attacks. Now, the ones which we are going to look at are the row hammer and some of the attacks which would impact the lifetime of NVMs. Okay, so I think with that I will pause this lecture. So shoot if you have any questions.
So in the side channel attacks, there can be multiple side channel attacks at the same time. Is there any example for it, or there cannot be multiple side channel attacks?
Multiple side channels means power and timing happening together.
Somewhat,
Is it?
yes.
Mm, frankly, I haven't come up with any works. I'm not
Across,
saying that there are no works, but at least I
mm,
haven't come across till now. Yeah,
uh,
go on.
acoustic and timing will be more easier, I guess.
Two stage, yes, and even acoustic and yeah, that's true. I'll stop the recording. So